For a problem like this, where we're given a description of a complex system of charged particles, the first thing I do is draw a diagram of the situation. The problem tells us that the three charges are oriented in a triangle shape, specifically an equilateral triangle, which means that every side of the triangle has the same length, d. Additionally, all three charges have the same magnitude of charge and the same sign of charge. They are all positive charges with a charge of capital Q. We're not actually given any numerical values here, meaning we're looking for a symbolic answer. We're looking for the magnitude of the electric field produced by the result of all three particles at any of the midpoints. I'll focus on this midpoint, at the bottom here, since from the perspective at which I drew this triangle, looking at the midpoint here makes it the most clear where any symmetries may be apparent. And there is a symmetry apparent, actually, because if we consider the definition of the electric field, we know that if we have a positive charge, then the electric field lines point outwardly away from that charge. And this applies in this situation, because if this is positively charged, which it is, then the electric field is going to be pointing rightwards at this midpoint where we're analyzing the charge, or the field rather. And the same thing applies to the charged particle on the right-hand side of the diagram. It is positively charged, so the electric field lines will be pointing away from it. So at this midpoint here, the electric field due to the right-hand particle is pointing to the left. Since all of the charges have the same charge magnitude, and since the charge on the left and the right-hand side of the triangle are equidistant from the midpoint, that means that their electric fields at the midpoint here are equal in magnitude, but opposite in direction, meaning they will effectively cancel each other out. Therefore, the net electric field at this point is due to nothing more than the single charge on the opposite side of the triangle, at the top of this diagram I've drawn here, meaning our calculations will work out quite smoothly. Recall that the electric field due to a point charge is equal to k, the Coulomb constant, times the charge, divided by r squared, where r is the distance between the point charge creating the electric field and the point we're analyzing, which is this midpoint down here. R, effectively, is this distance down the middle of the triangle. We need to find that length before we can proceed. Here is an enlarged version of half of the triangle above. Of course, d is the rightmost length here, the side length of the equilateral triangle. This bottom length here is half of the length of the triangle since we've bisected it. So this is d over 2, or half of d. The length on the left here is the length we want to find, r. Notice that this is a right triangle with a 90-degree angle, which means we can use the Pythagorean theorem. According to the Pythagorean theorem, the square of the hypotenuse of the right triangle is equal to the sum of the squares of the other two sides. So r squared plus the square of d over 2, or d squared over 4. Now let's take this equation and solve it for r. So r squared is equal to d squared minus d squared over 4. We can simplify this a bit by multiplying the numerator and the denominator of d squared by 4 so that the fractions line up, like so. And now we can subtract this more easily to find 3d squared over 4. We can now solve for r by taking the square root of both sides of the equation. So r equals d times the square root of 3 over 2. Now let's plug this into r for our electric field formula up here. Plugging this in for r and then squaring it, we end up with d squared in the denominator times 3/4. The 4, since it's a denominator under a denominator, can be pulled up into the numerator, and the 3 can stay in the denominator here. Finally, one last thing you can do, that I will do simply because it's sort of standard and professional to do so, is to rewrite k as 1 over 4 times pi times epsilon naught. And that's what I have done here. I don't think you're necessarily required to do so, but this is how electrostatic formulas are usually written, and that's what's standard. And that is our formula for the electric field at the midpoint of the triangle due to the three charges.